Hi grade 12s, welcome to Learn Extra. Today we're going to look at probability. Let's just break it down a bit and see what we're going to cover. In this lesson we're going to focus on revising the terminology. Now terminology, believe it or not, is extremely important. If you don't understand what the question is asking you, well then you're going to have a problem. Then we're going to use Venn diagrams, tree diagrams, contingency tables to solve our probability problems. And we're going to apply the fundamental counting principle to solve probability problems. But first of all, let's do a quick recap of what you already know. Right, the probability of an event taking place is always the total number of ways an event can occur over the total number of possible outcomes of an event. Now, normally what we do is we would say the probability of an event, and we would give it to you as a fraction form. So, for example, say I said to you the probability of throwing a 6 if we've got one die. Well, that would be easy. How many 6s do we have on the die? We only have one. How many possible outcomes have we got? We've only got 6 on the die, assuming it's a normal die, not something special. And so the probability would be 1/6. Right, then the next thing we need to remember is the probability of an event taking place ranges from the impossible at 0 to certain at 1. Now, you'll always hear them say, I'm sure you've heard people say, if you're going to have a baby, well, you have half a chance of getting a girl and half a chance of getting a boy. So, if it was certain, then we would be able to say, you're certainly going to have a girl, but we can't. What we can say for certain is something like, tomorrow the sun will rise. Okay, assuming nothing catastrophically happens, we will know that that will be true. We also know that we could say it certainly is not true. So there's a 0 probability that the world will remain dark for the next month, unless, as I say, there's some huge problem. So basically what we do is we work on a continuum of 0 to 1, where this is never going to happen, and this is always going to happen. So putting it in context of the die, if I said to you, we've got a normal die, what is the probability of throwing a 7? Now you know that that will never happen because the only ones you can have on the die are 1, 2, 3, 4, 5, and 6. So it's not going to happen. If I say to you, what is the probability of throwing a 1 or a 2 or a 3 or a 4 or a 5 or a 6? Well, then there's a certainty because those are the 6 outcomes. It's going to land on one of them, so you're going to be fine. Right, the following notations were introduced last year and will be used in the question. Now, I've already mentioned the first one. The P of A is the probability of event A happening. So if I was looking for the throwing the 6, I might say the P of a 6 or something like that. If I use P of A dashed, this means the probability of event A not happening. So going back to my example with throwing the die, I could say the probability of not a 6, well, there are 5 outcomes that are not 6. So my probability of not 6 would be 5 over 6, whereas the probability of a 6 is only 1 out of 6. So that's what we always talk about A complement. So when you see this, we are meaning A complement. And it's not saying you look pretty or anything like that. It just means the opposite of A. Right, then we had the notation, the probability of A and B happening is denoted by the probability of A with this like shape there, B. And what I'm telling you here is that that shape means and. Now, it's quite important that we understand the difference between and or. Just to put it in context, you want to go on a blind date and you say to your friend, whether it's a boy or a girl, I'd like this person you're arranging for me to be good looking and intelligent. So now you're being very fussy. You want both those characteristics in the person. If you say to them good looking or intelligent, well then you're happy to have someone who's good looking but not intelligent, or not good looking but intelligent. So it's less fussy and there are more members. Now it'll make more sense if I can show you on a Venn diagram. So this option here, probability of A and B would be this intersection. But this one, the probability of A or B, would be everything in those two circles. So a union, which is that U shape, means or and is not fussy, and the N shape is and it is fussy. I'm sure you remember that from last year, but I think a recap is never remiss. Now, the probability of event A happening, assuming that event B is taken as given. Okay, now, that is a conditional probability, so they would say the probability of A given B. That's how we'd represent that. Now, Venn diagrams are a useful way to represent all the events and calculating probability. Now, I've already mentioned a Venn over here. This is what I call a Venn diagram. And this little box thing would be the big set, and these little circles would be the smaller events. But we will be doing an example just now on Venn diagrams, so you'll see it in action. Tree diagram is a way of representing probability, especially for dependent events. Now, it can also work for independent events, but it makes more sense with a dependent. Basically, what I mean by a tree diagram is, say I have the probability of tossing a coin. And I can only get two outcomes on my coin. I can get a head or a tail. So I would go head or tail. But now if I'm going to toss the coin again, well, now I have a possibility of a head and a tail again, and a head and a tail. That's what I mean by a tree diagram. Now, contingency tables, a way to organize data when doing probability calculations. The kind of thing we're talking about here is you would get something like this. And say we would have men, women, total. And it would say be, I don't know, some two things we're looking at. So let's look at dark and fair eyes. And then what we would do is we'd say, okay, in our group of, say, 300 people, there are 120 men with dark eyes. There are 180 women with dark eyes. So altogether there are 300 people with dark eyes. And then let's say we've got 300 here, but this time we've got 240 men with fair eyes, but we will only have 60 women. And then if we wanted to carry on the total side of it, we would now say, well, in total we're dealing with 360 men, and with women we're dealing with 240, and altogether we have 600 people. So that's what I would call a contingency table. Nothing too serious to worry about. Let's have a look at the next set of information. Now, for example, here it says a card is drawn from a pack, replaced back into the pack, and a second card is drawn. Now, if you think about that, if I'm going to pull a card out, put it back, has anything changed? Is my cards the same as they were to start? And hopefully you all realize that, yes, of course it is. If I'm putting it back, nothing changes. Think about a game show and where you have, say, 4 red balls and 3 green ones. And you put your hand in and you pull out a red one, but now you put it back. So there's still the same amount of red balls as there was the first time, unless you don't put it back. So in this case, the card is drawn and then put back in the pack, and a second card is drawn. The possibilities which the card is drawn second is not affected by the first, and I think that is clear enough. The event of the 2 cards drawn are independent. In other words, the result of the first one does not affect the result of the second one. It would if I didn't put it back. So for example, back to that red and blue, if I've got 5 reds and 4 blues and I pull out a red, well, on my next draw, if I don't put it back, I've only got 4 reds and 4 blues. So there's now an equal chance of getting red or blue, whereas before there was a definite possibility of getting a red more than a blue. So this is the same thing. As soon as I put that card back in, it's exactly the same. If I don't put the card back in again, then there is a different thing. So when I put it back and nothing changes with my probability, like a coin, if I toss a coin, it's heads or tails. And it really doesn't matter how many times I toss that coin, I still have only 2 options of head and tail. Now, consider the example just mentioned. If the first card is not replaced, the possibility of the second card drawn is affected by the first. In this case, the card drawn the second time depends on the first one, and these events are called dependent. Now, obviously, In the first case where we put it back and nothing changed, it was independent. If I don't put it back, then it is dependent. Right, and then we have the addition rule, which you might remember from last year. It says the probability of A union B is equal to the probability of A added to the probability of B minus the probability of A intersection B. The easiest way to explain this is to use a Venn diagram. So I'm going to put a Venn diagram up here and show you what I'm talking about. So let's say that's A and that's B. Now, I'm saying A union B. Now remember, we talked about this earlier on, and I mentioned to you that A union B would be all of that. Now, if I'm going to use this rule, this addition rule, let's have a look what they're telling me. They're saying to me, well, it's the probability of A, so it's this whole set here, added to the probability of B, that whole set, minus one of these. Now, that makes sense because on the blue I counted that, and on the pink I counted that, so it makes sense I must take away that middle section because I've double counted it. Okay, but you can just learn the rule. And then it says, remember that if the probability of A intersection B is 0, then we have mutually exclusive events. In terms of a drawing, it would be something like this. There would be no common elements. An example of that would be your heads and tails, for example, or boys and girls. You're going to have a boy or you're going to have a girl, but there's not going to be something that is in between. Right, the complementary rule, events A and B are said to be complementary if the following is true. Firstly, they are mutually exclusive. And secondly, the probability of A added to the probability of B is 1, and this implies that they are exhaustive. So in other words, you can't have other options. So I go back to my example, the probability of a girl. There's one girl out of the two possible sexes. You can have a boy or a girl. And the probability of a boy, well, again, there's a boy out of two possibilities. If I add a half and a half, I'm going to get 1, which would mean that they are complementary, that they are mutually exclusive, and they are exhaustive. Okay, now let's look at the product rule. And the product rule says for independent events, the probability of A intersection B, or and B, is equal to the probability of A times the probability of B. Now this is going to be extremely useful because really when we are doing exam papers and we're setting test papers, often they will ask you, are the events mutually exclusive? Are the events independent? And you would have to justify. So you would, if you were showing that it was independent, you'd use this rule. And if you're showing they are mutually exclusive, the easiest one to use is this one over here. Okay, let's move on to the next, the actual questions and see how we do. Now it says, consider the sample space S of natural numbers less than 16. Right, so sample space is the big set. So a very good idea when you first start, obviously you're not first starting, so you would be all right with this, but if you were sort of revising it, maybe not a bad idea to do this, is to go along and to list your sample space. So S is equal to, notice the curly brackets, which means the set of, and along I go listing all these elements. Okay, and that's where I stop. Now it says that A is the event of drawing a multiple of 6. Now if we look at that S set, which of those numbers are multiples of 6? So if we go here, let's see what A would look like. Well, if I look at the set, I can see that the first multiple will be 6 times 1, and the next multiple will be 6 times 2, or 12. So there are only 2 elements that fall into the set of multiples of 6. Then it says B is the event of drawing a prime number. So right, B is a prime number, so let's get ourselves a color. So let's put B in here. A prime number, let's look, is 1 prime. Hopefully you guys are saying no, prime numbers have 2 factors, 1 and themselves. So 1 is not composite or prime. That's just something we've known for a long, long time. So B, the 2 is a prime, 3 is a prime, 4 is not, 5 is, 7 is, 8 isn't, 9 isn't, 10 isn't, 11 is, 12's not, 13 is, 14's not, and 15's not. So there we have those. And then the last set C, which we can make another color, the set C, is that we have an even number. So which of these are even numbers? Well, we've got 2, 4, 6, 8, 10, 12, 14. Now, as you can see, that there are elements that belong to A and B, or B and C, or whatever the case may be. There are overlaps on these sets. Right, so now what did the question ask me to do? So draw a Venn diagram to illustrate the events A, B, and C, and the sample space S. Right, so we have a spot over here, so let's put it in. Okay, we always make ourselves a nice little grid. This is S, the sample space, and we've got 3 sets. You know what, I'm just going to keep it the same color. We've got set A, set B, set C. Now, the first thing I would fit in first of all is what is common to all 3 sets. So if I go back there, well, 6 is not a prime, so it's not common to B, and 6 isn't even, but there's nothing that is common to all 3. So what I know is that this little section over here, which I'll just highlight, is going to be empty. Okay, which is absolutely fine, no problem with that. Now we start. 1 was not any of those. It wasn't even, it wasn't prime, and it wasn't a multiple of 6. So 1 is outside. 2 is even, and it is prime. So if you have a look there, 2 is even and prime, and it's not a multiple of 6. Anything else that is even and prime? No. So we know that even and prime, which is B and C, the only element there is 2 so far. Right, now 3 is a prime, but it's not even, and it's not a multiple of 6. 4 is even, but it's not a multiple of 6. 6 is a multiple of 6. So it goes between A and C. 7 is prime, so it lies over here. 8 is even, so it's over there. 9 is not prime, not even, and it's not a multiple of 6, so it's outside here. 10 is even. 11 is prime. 12 is even and a multiple of 6. 13 is prime. 14 is even. And 15 is not even, prime, or a multiple of 6. So that would be my Venn diagram. Very easy to draw. Okay, you can do it in any way you like. Like you're listing the sets is quite useful, and as you put them in, you underline them, so you make sure you've got everything there. We know we must have 15 numbers, so it's 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. So it looks like I'm missing one. I might have just missed one. Let me just check. 2, 4, 6, 7, 9, 10, 11, 12, 13, 14. Yes, I definitely have. I've got 1, 2, 3, 4. 5 is missing. 5 would be there. Okay, so we can run a quick check and make sure we haven't left anything off. Now, the first question says to me, what is the probability of something being in set A? Now, remember, the definition of probability is favorable outcomes over total outcomes. So how many total outcomes have we got? We've got 15 numbers. But how many are falling into set A? So if I look at set A, there it is. I can only see 2 elements in set A. So I can say the probability of A is 2 over 15. Now, the next one says the probability of not B. So in other words, it can be anything else but not in B. So in that case, let's highlight the not B in orange. There's B. So not B is everything out of the orange circle. So if we look there, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another way to do it is to count what is in B. So it's 2, 4, 6. I counted the 2 earlier, so that's a nice check. So I can see that if I count again, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of a possible 15. Now, this is quite a useful one to know, and I'm going to talk a little bit more about it. We would never leave our fraction as 9 over 15. We would always cancel it down. So we'd say 3 goes into 9 3 times, and 3 into 15 goes 5 times. So we'd rather write it as 3/5 rather than a fraction that is not cancelled down. Right, so let's just talk about what I was saying by an option. Now, the option would have been the following. To say, if I want b complement, remember that we said that the complement and the original add up to 1. So I could say to myself, the probability of b complement is equal to 1 minus the probability of b. So let's see how that works out. So 1 minus, what is the probability of b? It is 6/15. There are 6 elements in b, and there are 15 in total. So it's going to be 1 minus, and if we cancel this down, 3 goes into there twice, and 3 goes into there 5, and 1 minus 2/5 is 3/5. Does it agree? Yes, it certainly does. And that is very useful sometimes when you're working with a big set. It's easier to take away the little set so you can get it nice and easily. So just remember that little trick, it's worth it. Now they want the probability of A intersection B. So it's A and B. So let's take a color. A and B is this bit here. And you can see we have a technical hitch, because is there anything in there? Hopefully you can all see that there's nothing shared between A and B. So in other words, what I can do is I can say that will be 0, because there are no elements over 15, which is 0. Now, what did we say? If we said if the probability of A intersection B, then what was our rule? Let's go back to it and remind ourselves. Well, there it is. So what do we know? We know that they are mutually exclusive. Now, that's a good thing to bear in mind, and chances are somewhere along the line they're going to ask us something like that. So really, I know this means that they are mutually exclusive. Right, the next one says the probability of A union B. So now we want A and B together. So let's get ourselves another color. Let's take, let's try that one. A union C, was it? No, B union C. So B union C means all of those elements with all of those. So if you like, I can draw stripes or whatever in it, but I don't want to make the drawing look too messy. Right, now if I do that, it's all of that. So if I look at it, there are only 3 outside, 1, 15, and 9. All the others are inside, so there actually are 12 out of 15, which, if we cancel down, will be 4 over 5. Again, it's one where we could say 1 minus the complement of B union C. B union C is 3 over 15, which is 1/5, and you'll get the same answer. Right, the next one gets more exciting. It says A's complement intersected with B intersected with C. All right, so that makes life a bit exciting. So let's go back to the drawing. A's complement is everything that is not in A. So it would be all of these elements, and of course these ones outside as well. I'm just going to use this system to highlight it. So not A, so basically what I'm doing is I'm taking away the set A. Intersected with B. Now intersected with B would just be this part. Okay, just this little bit here. So let's put a blue ring around it so it makes it a bit better. Intersected with C. Well, intersected with C is only this one here. So it's just 2. So in other words, we only have one solution here out of 15 that will work in that category. Now, it does help to draw pictures or to use color to shade in, so it's easy to pick out your answer. Right, and here comes the million-dollar question. They say, are A and C mutually exclusive events? Give a reason for your answer. Now, we know they're mutually exclusive. If the probability of A intersection C is 0, so let's go and look. What is A intersection C? Well, A intersection C is not 0. A intersection C is that bit, and there are 2 elements. So we have 2 out of 15, and therefore not mutually exclusive. As we have an intersection. Okay, so that's clear enough, I'm sure. Now it says, are A and B independent events? Give a reason for your answer. Right, so remember, for independent events, we know that the probability of A intersection B is equal to the probability of A times the probability of B. So what I would do is I'd tell the examiner, for independent events. Now what I would do is I'd start on the left-hand side. We know that the probability of A intersection B was 0. So the left-hand side would be 0. The right-hand side, we would say the probability of A, which we worked out earlier to be 2/15, times the probability of B, which is going to be 2/5. And I think you can see the answer to this already, because we got 4 over 75, I think. Now, clearly, left-hand side is not equal to right-hand side, and therefore not independent. Now, think about it. What did those two sets represent? A was the multiples of 6, and B was the prime numbers, if I remember rightly. So what are they doing? They're saying, are they independent of each other? And according to my rule, it's no. Right, let's move on to the next question. And this one is another Venn diagram. Now, another way they like to ask the Venn diagram, the first way is like I've shown you now, where we put the values in and we come up with a solution. But this time now, I've given you the probabilities, okay, and now I'm going to ask you to fill in the rest of the drawing. So, right, you'll see they've given you part of it. They've said the probability of not A is 0,3. So in that case, what would the probability of A be? Remember, probability always adds up to 1. So if not A is 0,3, A must be 0,7. So that's a much easier one to work with. So I'm going to work with this one, and this one is 0,2. I'm going to write it alongside. It's just easier to refer to. Now it says refer to the sketch. There's my sketch. Well, they've told me that the probability of B is 0,4. The probability of A is 0,7 we've worked out. And the probability of A intersection B is 0,2. Notice over here they've got a 0,1, which means the 0,1 does not belong to either A or B. Now, what do we know about probability? We know that everything must add up to 1. So in this case, we need to go and work. Now, I'm sure they're going to ask me to find X and Y. Let's see. Yes, it says find X and Y. Now, X is going to be easy because we know it. It said the probability of A intersection B is 0,2. So X is going to be easy. It's 0,2. Let's check this out and make sure we're right. If I look at this, 0,2 and 0,2 adds up to 0,4. Yes, it makes perfect sense with that drawing. Right. Then they said to me the probability of A is 0,7. So we know that this little circle over here is 0,7, but we've got 0,2. So this must be 0,5. Now we know that if we are right, everything in that square sample space must add up to 1. Let's see if it's true. Well, let's see. It's 0,2, 0,2, so it makes 0,4. Added to 0,5 makes 0,9. Added to 0,1 gives me 1. So yes, we are sure we're right. So the X was 0,2 and the Y was 0,5. Let's see what they ask us further. If the universal set contains 100 items, find out how many elements were in set B. Remember, N stands for number of elements. And this is actually the N of the sample. N of the sample is 100. That's what they're telling me. So if I look at B, B was equal to 0, sorry, not N, the P of B was 0,4. So, in other words, we could say 4 in 10 is B, or better still, 40%. Remember, when we represent probabilities, we can represent them as fractions, decimals, or percentages, just depending what the question's asking. So rather than 0,4, I'm going to rather say 40% of the people were in B. So in this case, or whatever they are, they might not be people, the number in B, if there are 100 items, must be 40 people. What happens if I set you the universal set? Universal set just means the sample space. But say I said to you there are 500 items. Well, once again, I'd have to work out what 40% was of 500. So doing that, I would end up with 200. So there would be 200 items in set B. So don't let that put you off. Just remember, it's the proportion that belongs to B. Okay. Let's see what the next one brings. Now, this next one is a lovely little question, also very, very common in an exam. It says, in a factory, 3 machines, A, B, and C, are used to manufacture plastic bottles for tablets. They produce 20%, 30%, and 50% are each of those respectively. Respectively just means in the same order as the top over there. Right, so 1%, 2%, and 6% respectively, so this belongs to A, this belongs to B, and this belongs to C, of the plastic bottles produced by the machines are defective. Okay, so that's just information. Represent the following information by means of a tree diagram. Clearly indicate the probability associated with each branch of the tree diagram. Now, I personally love a tree diagram. So for me, the first thing I would do is start to unpack the thinking. They told me there are 3 kinds of bottles. So let's put the drawing over here, I think. So I know I can have bottle A, I can have bottle B, or I can have bottle C. The chances of getting bottle A is 20%, or if you like, 0,2. Because remember, we talked about 20% is equal to 20 over 100, which is equal to 0,2. And you can decide whichever one you fancy to use. In this case, I think I would use decimals. So doing that, I go to B now, and they say it's 30%, so that's going to be 0,3. And to get C is 0,5. Now, a very important thing with the tree diagram is you always check on any arm set that adds up to 100%. So does it? 0.2, 0.3, 0.5, it gives me 1. So yes, that's correct. That's all we have. We only have 3 bottles. We don't have any others. Right, so what else do they tell me? They tell me 1% are defective in A. So this is going to be the next branch of my drawing. So defective, not defective, defective, not defective, defective, and not defective. Right, so 1%, remember how we did it? It's 1 over 100, which is going to be 0,01. So it's 0,01. Now, obviously, if 1% are defective, then 99% is not defective. So this R must be 0,99. Let's do this one in a different color so it stands out a bit more. Now, in bottle B, 2% were defective, so 0,02 defective, which means 98% must be not defective. And the last one here is this one. And here we have 6%, so we have 0,06. And over here we have 0,94. Right, so that's my tree diagram drawn. Right, the next question says, a plastic bottle is selected at random from the total production. So we're going to put our hands in, pull out a bottle, and who knows if we're going to get A, B, or C. What is the probability that it will be produced by machine B and not defective? Now, what we do for this is we follow the arms. So they wanted to come from B. So let's get a little highlighting color. I don't know what we'll use. Let's use orange. So it must be B, and it must be not defective. So I'm interested in that arm. And so for B, I'm going to say 0,3 is the probability of getting B, times by 0,98 not defective. And now it would be a matter of doing this multiplication, which we can do on our calculator, but it's not that bad. It's going to be 2940,294. Okay, so we have that probability of getting a bottle from B that is not defective. Obviously, if we were looking for a bottle from B that is defective, it would be smaller, but I don't think they're asking us that yet. Right, so that's easy enough. The second thing is, what is the probability that the bottle is defective? So now they're saying, look, it doesn't matter where this bottle comes from, whether it's A, B, or C. We just want to see the probability of it being being defective. Let me just check I'm not lying to you. The bottle is defective. Yes, that's what we want. So now we go to our drawing and we're going to pick up all the defective bottles. So if we do that, let's get ourselves a little stripy line. So if I choose A, I must get defective there. If I choose B, I must get defective there. And if I choose C, I must get defective there. So right, in the light of that, let's get ourselves a pink one. We have several we're going to add together. So what I'm saying is when we're on the branch, we multiply, but between the branches we add, and I'm going to show you why I'm saying that in a moment. So if I start with the probability of A defective, added to the probability of B defective, added to the probability of C defective. Let's see what we're going to get. So the probability of A defective would be 0,2 times 0,01. Added to the probability of B, which is 0,3 times defective 0,02. And then the probability of C is 0,5 times the probability of it being defective, which is 0,06. Okay, so now we're going to work this out. So we're going to get 0,002. Of course, your calculator can do all this sort of stuff for you. 0,006 and 0,03. And if we add those together, we're going to get 0,038. So the chance of getting a defective bottle is very, very small. If we think about our little number line between 0 and 1, you can see that an answer like this would be pretty close to this end. So it's not very, very easy to get a defective bottle, even if you're choosing from any of the bottles. So it makes perfect sense. Now, what was I trying to stress? What I was trying to stress is something important. We know that this is going to be 0,002. This one was 0,006. And this one was 0,003. We had worked out this other one over here in this little lane here at 0,294. And what I'm saying to you is if we now go and we work out this one, and we add these together, we must get 1. And that's what's important about these. We can always check ourselves. If we work them all out and we see that they add up to 1, then we know that every selection we've made has been correct. Okay, so I think that's a very good point for us to take a bit of a break, and we'll pick up from there a little later. Welcome back. We are going to look at our next question. And as you can see, it's talking about a plastic container of tablets that contains 3 pink, 2 green, and 5 blue tablets. So they're saying, here's my container inside of those tablets. And it says to me, 2 tablets are removed successively without being replaced. So I'm going to put my hand in, pull out a tablet, eat it. Then put my hand in, pull out a tablet, and eat it. Let's hope is what I need. But I'm not putting it back. So every time I pull out a tablet, the probability of getting something changes. Now, before we even engage with the question, let's first see how we can represent this information to make it easy for us to understand. Now, I'm sure you are all thinking to yourself, this is a great opportunity for a tree diagram, and you are quite right. This is a great opportunity for a tree diagram. So let's have a look how our tree would look before we even start to look at the question. And I've used the spotty one, but I'll change that just now. How many greens have I got? There are 2 greens. And I then have 5 blues. Right, so if I'm going to represent it in a tree diagram, basically what I'm saying is I could have drawn out any of these colors immediately. So if I drew a pink, in total I've got 10 tablets in my tub, and there are 3 that are pink, so my probability is 3 out of 10. So I can make this 3 out of 10. Right, then I go to my green one, and there are 2 greens, and I remember this is the first tablet I'm drawing out, so nothing has changed yet. I have 2 green tablets. I have 2 favorable outcomes out of a total of 10. And then my last option is to draw a blue. And again, it's the first draw, so I've still got my 5 blues there, so I can choose 5 out of 10. Now, I'm sure you're thinking to yourself, oh, but she told us never to leave a fraction uncancelled. Yes, that is true, but I'm meaning in the answer. On the actual arm, it's a good idea to keep it in the form it is. It makes your arithmetic a lot easier, as you'll see in a little while when we do the question. Right, so now we've taken this first tablet, and now we're putting our hand in to take our second tablet. So again, I can draw a pink. If I've chosen any of those as the first one, I can draw a green, and I can draw a blue. Now, obviously, if I was drawing a third tablet, I would have problems with my green one, because the green has only got 2 tablets. So if I should take a green and then take another green, well, then there are no more greens left. So that arm would die if I was carrying on with the question. But fortunately, we're only drawing 2, so it's not going to cause us big problems. So let's have a look at what we've got here. Right, I just think I need to get rid of this little green over here so we've got some room. And let's start by looking at the pink. Now, if our first tablet I ate was a pink, that means instead of 3 pinks, I've only got 2 pinks left. So in actual fact, to get a pink now is 2 out of 9, because I have already eaten a pink. Now, obviously, if I've taken a green as my first tablet, I still have the 3 pink tablets. So now I have 3 out of 9 chances of getting a pink. And if I took a blue as my first choice, means that I also have a 3 in 9 chance of drawing a pink. Right, now we go to the green. If we look at the green, if I drew a pink as my first one, the greens have not been affected. So I've still got 2 greens I can draw. But if my first tablet was a green, I only have 1 of them left in the second tablet. And then the last one, again, I didn't draw a green to start, so I still have 2 of these available. Just before we move on any further, do you agree with me that 3 tenths, 2 tenths, and 5 tenths added together would give me 1 10 tenths? And remember what I said to you about them adding up? They will always add up to 1. Let's go and look at the blue now. If we look at the blue here, I haven't had a blue, so I still have 5 in 9 ways of choosing that. Let's check. 2 plus 2 plus 5 makes 9 ninths, that's 1. Over here, I haven't had a blue yet, so I still have 5 ninths of a way. So 3 and 1 is 4, and 5 is 9, so that's adding up beautifully. And then over here, and I just see I've left off my green over here, although I did draw it green. Here, I've eaten a blue, so that means I only have 4 blues left. So I have 4 in 9 chances of getting a blue. Now, if I'm looking there, 3 and 2 is 5, and 4 is 9. So yes, that adds up to 1 as well. Now, remember what I said to you. I said the probabilities must always add up to 1. Now, they've done that beautifully for us all the way through. So let's start by looking at the probability of a pink and a pink. Now, remember what I said to you when we are doing and, we're going on the arms of the tree and we're multiplying. So we're saying 3 tenths times 2 9s. And again, I'm not going to cancel it down just because it makes it easier for us to work with it just now. So it's going to be 6 90ths. And then we are going to go for the next one, which is pink and green. So the probability of a pink and a green. The probability of the pink was 3 10s. And the probability of the green was 2 9s. So again, it's 6 90ths. Of course, we can cancel down. We'll talk about that in a little while. Right, the next one is the probability of a pink and then a blue. Now, the pink, as I said to you, was 3 10s, and the blue was 5 9s. So that is equal to 15 90ths. Now, at the moment, that does not add up to 1, but when I'm finished working them all out, that will add to 1, and I'm going to show you that. We're going to use it to answer some questions now, so it's not a waste of time to do it. I'm going to add some questions in as well. Now, over here, the probability of drawing a green and then a pink. And I should have had the pink in pink. The probability of the green is going to be 2 10s times the probability of the pink, which is 3 9s. Which gives me 6 90ths. Now, I think you can see why I was keen to keep them uncancelled, because it's just going to be easy to add them if they're all over 90. It'll be very simple. Right, the next one is the probability of drawing a green and a green. And if we do that, it would be the 2 10s times the 1 9th, which is going to be 2 90ths. Right, and then the next one is the probability of green with blue, which is equal to 2 10s times 5 9s, which is equal to 10 90ths. Right, now we're going to the last little arm, where we had the probability of drawing a blue and then a pink. Well, the probability of the blue was 5 10s times the probability of the pink, which was 3 9s, which is going to be 15 90ths. Right, then we have the probability of a blue with a green, which is equal to the probability of the blue was 5 10s, and the green is 2 9s. So that's going to give me 10 90ths. Right, and then the last option is the probability of drawing a blue and then another blue. Well, that's going to be 5 10s times 4 9s, which is going to be 20 90ths. Okay, so if we look at this, we've got 6 and 6 is 12. 15 onto that's 27, 33, 35, 45, 50, 60, 70, 80, 90. And yes, that makes sense. 90 90ths is actually 1. So it makes perfect sense that that is the right answers, because we know everything adds up to 1. Let's go to our actual questions now and see what they're asking. They want to know what is the probability of them both being blue. So the probability of blue, blue. Well, that's going to be easy enough. Blue, blue, there's only one case of that. There it is. And we can see it is 20 90ths. Now, this is where I would say you have to cancel down. So you wouldn't leave your answer as 20 90ths. You'd write it as 2 9s, because that's a much nicer, neater fraction than the unsimplified one. Now it says, and this is the interesting one, the probability that at least one pink tablet is selected. Now, if I say at least one, that means 1 or 2. The only one I'm not interested in is when there's no pink at all. Okay, so now what we're going to do is we're going to go to our tree diagram. And we're going to say, okay, we are interested in, and let's take the orange pen, that there must be at least one pink. So it would be this one, this one, this one, this one, and this one. The ones that are not involved are the 2 here and the 2 there, because there are no pinks. So there are actually 5 possible answers for at least one pink. So if we go back to our actual working here, Okay, remember we were interested in the probability of at least one pink. We had pink and pink. Added to the probability of pink with something, the probability of pink with something, added to, and I'm just going to quickly put this down, the probability of something pink, and added to the probability of something pink. Right, then all we're going to do is we're going to go along and we're going to do them. So we're going to say that's blue, this one's green, and this one's green. And we're going to add them together, because remember what I said to you about the arms on the tree diagram? If we're going to take the answers between the arms, we add them. When they're on the arms, we multiply them. So right, the probability of pink and pink is 6/90. Pink and green is 6/90. Pink and blue is 15/90. Green and pink is 6/90. Now you can see why I also said to you leave it as uncancelled. It just makes it so much easier, and that is 15/90. Now they're all 90ths, they're easy to add up together. So what we can do now is we can say 6 and 6 is 12, plus 15 is 27, 33, 38, 48 over 90. And now again, that is not simplified form, so we're going to actually simplify it. And we can see that we can take 2 into both of them, so we're going to get 24 and 45. If we take 2 into there, we're going to get 24, 2 into there, 45. And over here, I can take 3 into there, giving me 8, and 3 into there, giving me 15. So the chances of getting at least one pink pill is quite high. It's 8 over 15, which is nearly, well, it's more than half, just over a half. So we've got quite a good chance of getting a pink tablet, at least one. Of course, there was another way you could have done that. You could have said 1 minus all the ones that are not having any pink in them. And then you'd only have 4 to add, but really it didn't make a difference here. What I want to do is add one more question to this, which people like to ask. And let's call it number 3. It's not on the notes, but I'm going to put it in anyhow. They would say, what is the probability of both tablets being the same color? So now I'm not fussy. I'm saying, well, maybe they are green, green, or blue, blue, or pink, pink. But as long as they're both the same color, let's see what chance we have of that happening in our lives. So we have the probability of pink, pink, added to the probability of green, green, added to the probability of blue, blue. Now blue, blue, I can see here, it's 20/90. Green, green was 2/90. So let's just change the pen. And pink, pink is 6/90. Now if I add that up, 6 and 2 is 8. 8 and 20 is 28 out of 90. And if we cancel 2 into that, we'll go into there 14 times. And 2 into there will go 45. And that's as far as we can go, 14 45ths. Now, if you look at that, that is approximately almost 30%, 33% round there. You can take and work it out in your calculator. So I'm saying the chances of getting 2 the same color is not as good as getting at least 1 pink. So it's interesting to think about these things, because I don't think we do think about it. I'm sure you've seen hundreds of questions already where it's a sock drawer and you lean over and you pull a sock out and what are the chances of getting the same color. They love these kind of questions. Now there are other ways we could have represented these answers. We could have put them into kind of table. So that's quite a nice thing to look at. So what we could do is we could do something like this. I don't know if I'm going to pursue it right the way down. So say I say pink, pink. Let's take green, green. And last but not least, blue, blue. And we could have represented all of those probabilities we got in this table. So we could say the probability of BB was 20/90. For B and G was 10/90ths, 15/90ths. So you can see I can summarize it beautifully on a table. And that could be quite useful on occasions. Then it's green with blue. So that one there would be 10/90ths. This next one would be 2 and 6. So 2/90ths, 6/90ths. And then the pink ones were 6, 6, 15. 6/90ths, 6/90ths, and 15/90ths. So if I asked you the question now and I said probability of pink, pink, green, green, blue, blue, well, it would be easy enough. You would go along and say pink, pink is this one, green, green is this one, and blue, blue is this one. Let's add them together. Or if I said to you the probability of at least one pink, we could go along and say, okay, it would be this, this, this. It would be this, and it would be this, and you'd be able to work it out. So it would be a nice way to represent your answers. So something worth thinking about, give it some thought, see what you prefer to do. I really enjoy my tree diagram. I always find it very, very useful. Right, let's have a look at the next question. Right, these are also my favorites. It seems like everything's my favorite. It says, consider the letters of the word distillation. In how many distinct ways can the letters be arranged? Now, when we've got letters to arrange, we're not saying making words, and if we did say making words, it need not be words that make sense. The best way to do it for me is to sort the words so that they're the same. So I know that there's only one D here. There's an I, there's an S, there's a T. Now this I I'm going to put next to this one. L, L. I've got to have an A, I've got to have a T, I've got to have another I, I've got to have an O, and I've got to have an N. So there's the words, so D-I-S, T-I-L-L-A, T-I-O-N. So that's definitely the words. Now why I do that is it helps me to see how many times that letter has been repeated. Sometimes the word is a word you're familiar with, like mathematics or trigonometry. You know, maths people, we always like to use our own things. So this is a bit of a different word. Maybe if you do science, it's not such a different word for you, or life science. If we have a look there, how many ways can it be arranged? So the first thing I would do is I'd say to myself, how many letters are there altogether? I've got 2, 4, 6, 8, 10, 12. So there would be 12 factorial ways. However, the T's are not distinguishable from each other, nor are the I's, nor are the L's. So we can't tell the difference between one L and another L. So I have to divide by the repetitions. So in this case, the I repeats 3 times, the T repeats twice, and the L repeats twice. So that gives me that. And now it would be a matter of sticking it into my calculator and getting an answer. So let's pull the calculator up. We've got 12, so it's shift, there's the factorial, and I must divide by, and I'm going to put it in brackets because I want to divide by all of this, 3 factorial times 2 factorial times 2 factorial, close my bracket, and my answer comes out. And it's a delightful little answer, as you can see. It's 199,584,00. So there are lots of ways we can arrange those letters, and we have taken into account the repetitions. Okay, before we move off it, I just want to spend a few seconds in case you've forgotten. Remember, if I say 12 factorial, what it means is 12 times 11 times 10 times 9, all the way till I get to times 1. Now, of course, to work that out mentally is not fun and not advised, okay? So definitely this is a case where the calculator is essential. If it was a small number, sure, work it out, but that is not a small number. Right, let's look at the B question. The B question says, what is the probability that the 2 L's are not together? Now, the best way to do it if they say not together is to put them together. So let's say, what is the probability of the 2 L's together? because that's the very thing I want to avoid, but it's easier to put them together than to separate them. Right, now if I am putting them together, going back to our little drawing over here, in effect, I'm putting them as a parcel. Remember, I've said to you that the one L is not different to the other L. So it's not like, I'll do a question just now with a little bit different where it is important, but in this case, the L's are the same. So what I can do now is say, instead of having 12 letters in this word, I now have 4, 5, 6, 7, 8, 9, 10, 11 letters. So in actual fact, I would have 11 factorial, but now in the repetitions, the L's are not repeating because they're together. So it would just be 3 factorial over 2 factorial. Okay, now that's the number of ways I have of getting the L's together. Now, of course, it's a probability, so I have to divide it by all the possible ways I have, which is this answer I had earlier on, the one I found in A. So I need to go and work this out. So I'm going to pull the calculator up again, work it out, and then we're going to talk about it, and we're going to get an actual answer. So let's pull the calculator up. What I'm going to do is I'm going to store in, say, let's put it in A. So we've got it there. Okay, and it's in there. So now I can clear the calculator, and I can do the other one. So I'm going to go 11, shift factorial, divided by, open the brackets, 3 factorial times 2 factorial, and close my brackets. If it'll let me. And I press the equal sign, and there's my answer. It's going to be 3326400 over the one I had earlier on, which is this delight. Now what I'm going to do is I'm going to take that and just divide by the memory. So I divide by recall A, which equals, oh dear, I don't think it saved my number, so let's just do it properly. So it's 3326400 divided by 19958,400. And I'm going to get the answer 16, which is a really nice answer. Now remember, that was the probability of having the L's together, but the question was not that. The question was, what is the probability that the two L's are not together? So all we would do now is we would say the probability of the two L's not together, T-O-G-E-T-H-E-R, can't spell today, will be, the probability is 1 minus 1/6, so the answer is 5 sixes. So there's quite a good chance that my two L's will not be together. Now I could get carried away and I could say to you, okay, what is the probability of all the repetition letters being together? Well, that's not going to change how I do it. So now what I would do is I would say, okay, I'm going to make a bundle of the T's and a bundle of the I's. So now I have 1, 2, 3, 4, 5, 6, 7, 8 letters. So I would say 8 factorial. And then there would be no repetitions, so I would simply divide by my original number, which was that delight, 199,584,400. Okay, and I'm not going to even go into that because you can see it would be even easier if I said that none of them. But what I could ask you, which is quite a nice question, is what is the probability of the letter starting and ending with a T? Now, as soon as we do that, it's quite nice. So let's go back to it. I want it to start and end with a T. So I want the T in the front and the T in the back. In other words, the T's are no longer part of the deal. They've been placed and they cannot be moved. Then the rest of them, the other 10 letters in between, that's 5, 6, 7, 8, 9, and I need one more 10. Okay, those can be moved around. So what I would do in that case, this is just a little bit of an extra aside, I would say, right, that means I've got 10 letters I have to place, and I've got repetitions on I and repetitions on L. So it would be 3 factorial, 2 factorial. And that would be if it starts and ends with a T. That's the number. If I want the probability, I would divide by the total number of words I could make. So you can see that even if I start changing around things, it's actually very nice to work with and fun. Just one thing I want to mention, which is quite important. It's got nothing to do with this particular question, but I'm just going to mention it because it's worth knowing. Supposing we are going to movies, and there are 6 friends. It's couples. So we've got a boy and a girl, boy and a girl, boy and a girl. And we get to the movies, and we've booked these 6 tickets, and we want to work out how many ways we can put these people in the seats. Well, that's going to be easy if we don't care if boyfriends and girlfriends sit together. So if we don't worry, the number of ways of sitting the people who are going to movies, so the number of ways, we would say there are 6 ways we can choose this first person, but once the first person is seated, there are only 5 ways of choosing the next one. Once that person's seated, 4, once that person's 3, one person 2, and one person 1. So that's going to be very easy. It's going to be 6 factorial, which we can all work out. However, say I say to you, the couples want to sit together. So in actual fact, remember how we bunched the letters? We're going to do the same with a couple. So we've got the A girl and the A boy, the B girl and the B boy, and the C girl and the C boy. So now we're going to make them a couple, and we want them to sit together. So in actual fact, we have 3 factorials of placing them here. So we could put the first couple in there, the second couple in there, and the third couple in there. But I didn't say it has to be girl, boy, girl, boy, girl, boy. So I could have the boy and the girl, boy and the girl. I could go boy, girl, girl, boy, boy, girl, or something like that. So what I have to introduce is 2 factorial, because these are different. They are a couple, but the boy is not the girl and the girl is not the boy. So then the order is important, unlike this previous question, where I've said that L's are not distinguishable, T's are not distinguishable, and the I's are not distinguishable. But if I was placing people in seats, then it did matter where I put the boy and the girl. So if I had a girl here and boy there, it would be a totally different arrangement if I now put my boy here and my girl there. So I've got to take that into account. So that's why I times by 2 factorial, because each of my couples can be rotated. So I just wanted to mention that just so you know that that can happen. With words, with letters on the alphabet, there's not a problem. Right, so I hope this has helped you to sort of put this in perspective. It's a wonderful little section, lots of fun, and it's really nice when you're watching a game show and you're watching them happen. You can actually look at what the chances are of something happening. And I'm sure you've seen many game shows on TV where they have to draw things out or spin things or whatever. And you can use your probability to look at that. And it's lots of fun. Anyhow, I hope you've enjoyed it, and hope you're feeling good about your probability. Bye-bye. As a card is drawn from a pack, replaced back into the pack, and a second card is drawn. Now, if you think about that, if I'm going to pull a card out, put it back, has anything changed? Is my cards the same as they were to start? And hopefully you all realize that, yes, of course it is. If I'm putting it back, nothing changes. Think about a game show and where you have, say, 4 red balls and 3 green ones. And you put your hand in and you pull out a red one, but now you put it back, so there's still the same amount of red balls as there was the first time, unless you don't put it back. So in this case, the card is drawn and then put back in the pack, and a second card is drawn. The possibilities which the card is drawn second is not affected by the first, and I think that is clear enough. The event of the 2 cards drawn are independent. In other words, the result of the first one does not affect the result of the second one. It would if I didn't put it back. So for example, back to that red and blue, if I've got 5 reds and 4 blues and I pull out a red, Well, on my next draw, if I don't put it back, I've only got 4 reds and 4 blues. So there's now an equal chance of getting red or blue, whereas before there was a definite possibility of getting a red more than a blue. So this is the same thing. As soon as I put that card back in, it's exactly the same. If I don't put the card back in again, then there is a different thing. So when I put it back and nothing changes with my probability, like a coin, if I toss a coin, it's heads or tails. And it really doesn't matter how many times I toss that coin, I still have only 2 options of head and tail. Now, consider the example just mentioned. If the first card is not replaced, the possibility the second card drawn is affected by the first. In this case, the card drawn the second time depends on the first one, and these events are called dependent. Now, obviously, when the first case where we put it back and nothing changed, it was independent. If I don't put it back, then it is dependent. Hi grade 12s, welcome to Learn Extra. Today we're going to look at probability. Let's just break it down a bit and see what we're going to cover. In this lesson we're going to focus on revising the terminology. Now terminology, believe it or not, is extremely important. If you don't understand what the question's asking you, well then you're going to have a problem. Then we're going to use Venn diagrams, tree diagrams, contingency tables to solve our probability problems. And we're going to apply the fundamental counting principle to solve probability problems. But first of all, let's do a quick recap of what you already know. Right, the probability of an event taking place is always the total number of ways an event can occur over the total number of possible outcomes of an event. Now, normally what we do is we would say the probability of an event, and we would give it to you as a fraction form. So, for example, say I said to you the probability of throwing a 6 if we've got 1 die. Well, that would be easy. How many 6s do we have on the die? We only have 1. How many possible outcomes have we got? We've only got 6 on the die, assuming it's a normal die, not something special. And so the probability would be 1/6. Right, then the next thing we need to remember is the probability of an event taking place ranges from the impossible at 0 to certain at 1. Now, you'll always hear them say, I'm sure you've heard people say, if you're going to have a baby, well, you have half a chance of getting a girl and half a chance of getting a boy. So, if it was certain, then we would be able to say, you're certainly going to be doing an example just now on Venn diagrams, so you'll see it in action. Tree diagram is a way of representing probability, especially for dependent events. Now, it can also work for independent events, but it makes more sense with a dependent. Basically, what I mean by a tree diagram is, say I have a probability of tossing a coin, and I can only get 2 outcomes on my coin. I can get a head or a tail. So I would go head or tail. But now if I'm going to toss the coin again, well, now I have a possibility of a head and a tail again, and a head and a tail. That's what I mean by a tree diagram. Now, contingency tables, a way to organize data when doing probability calculations. The kind of thing we're talking about here is you would get something like this. And say we would have men, women, total. And it would say be, I don't know, some 2 things we're looking at. So let's look at dark and fair eyes. And then what we would do is we'd say, okay, in our group of, say, 300 people, there are 120 men with dark eyes. There are 180 women with dark eyes. So altogether there are 300 people with dark eyes. And then let's say we've got 300 here, but this time we've got 240 men with fair eyes, but we'll only have 60 women. And then if we wanted to carry on the total side of it, we would now say, well, in total we're dealing with 360 men, and with women we're dealing with 240, and altogether we have 600 people. So that's what I would call a contingency table. Nothing too serious to worry about. Let's have a look at the next set of information. Now, for example, here to have a girl, but we can't. What we can say for certain is something like, tomorrow the sun will rise. Okay, assuming nothing catastrophically happens, we will know that that will be true. We also know that we could say it certainly is not true. So there's a 0 probability that the world will remain dark for the next month, unless, as I say, there's some huge problem. So basically what we do is we work on a continuum of 0 to 1, where this is never going to happen, and this is always going to happen. So putting it in context of the die, if I said to you, we've got a normal die, what is the probability of throwing a 7? Now you know that that will never happen, because the only ones you can have on the die are 1, 2, 3, 4, 5, and 6. So it's not going to happen. If I say to you, what is the probability of throwing a 1 or a 2 or a 3 or a 4 or a 5 or a 6? Well, then there's a certainty, because those are the 6 outcomes. It's going to land on one of them, so you're going to be fine. Right, the following notations were introduced last year and will be used in the question. Now, I've already mentioned the first one. The P of A is the probability of event A happening. So if I was looking for the throwing the 6, I might say the P of a 6 or something like that. If I use P of A dashed, this means the probability of event A not happening. So going back to my example with throwing the die, I could say the probability of not a 6, well, there are 5 outcomes that are not 6. So my probability of not 6 would be 5 over 6, whereas the probability of a 6 is only 1 out of 6. So that's what we always talk about A complement. So when you see this, we are meaning A complement. And it's not saying you look pretty or anything like that. It just means the opposite of A. Right, then we had the notation, the probability of A and B happening is denoted by the probability of A with this like shape there, B. And what I'm telling you here is that that shape means and. Now, it's quite important that we understand the difference between and or. Just to put it in context, you want to go on a blind date and you say to your friend, whether it's a boy or a girl, I'd like this person you're arranging for me to be good looking and intelligent. So now you're being very fussy. You want both those characteristics in the person. If you say to them good looking or intelligent, well, then you're happy to have someone who's good looking but not intelligent, or not good looking but intelligent. So it's less fussy and there are more members. Now it'll make more sense if I can show you on a Venn diagram. So this option here, probability of A and B would be this intersection. But this one, the probability of A or B, would be everything in those two circles. So a union, which is that U shape, means or and is not fussy, and the N shape is and it is fussy. I'm sure you remember that from last year, but I think a recap is never remiss. Now, the probability of event A happening, assuming that event B is taken as given. Okay, now, that is a conditional probability, so they would say the probability of A given B. That's how we'd represent that. Now, Venn diagrams are a useful way to represent all the events and calculating probability. Now, I've already mentioned a Venn over here. This is what I call a Venn diagram. And this little box thing would be the big set, and these little circles would be the smaller events. But we will